Hi, I'm Beth Faber from the Hydrologic Engineering Center, and this is part one of Analyzing Hydrologic Time Series. This is lecture 4 in the class on statistical methods in hydrology. This is part one of four parts, meaning 4 videos. So you should find 4 videos for this lecture. This lecture is bit of a review and connect the dots on some topics that we saw in the introduction and in parametric modeling, a bit of a very brief introduction to a topic, and then some new material. The material in this lecture is broken up into topics based on the time period and on whether we evaluate all the data or just isolate extremes. The relevance of isolating extremes is in the assumptions that we can make on our data set and thus the type of analysis we can do, right? So if we're isolating annual extremes, there's enough time between data points that we can generally assume independence of our data points and do a type of frequency analysis that we saw in the introduction and parametric modeling lectures. Right. We'll only do a very brief mention of partial duration series. These are also extremes, but rather than the largest value in each year, it's all values over a particular threshold. And if we choose that data set carefully, we can again assume independence. And then we move on to when we use all of the data. Daily flows cannot be considered independent of each other. They're persistent. Today's flow has quite a bit of dependence on yesterday's flow. So we use different approaches. We're going to talk about duration curves and summary hydrographs. And then finally, if we accumulate into annual volumes, again, we have persistence, and we're going to look at some modeling of dependent random variables and use that as a chance to talk about drought. So in this first video, we will talk about instantaneous annual maximums. We'll look at unregulated and then regulated flows. And with unregulated flows, we'll take a moment to talk about Bulletin 17b. So this is a time series of flow on the American River in California. This is 108 years of record. In order to have 108 years of unregulated flows, the first half of the record is just gauged flows, and then a reservoir was constructed in the mid-50s, and so the second half of the record is back-calculated unregulated flows based on inflow to the reservoir routed down to the gauge site. When I say unregulated flows, I just mean flow without human interference, and so we had to back out the influence of the reservoir here. So to start with an annual maximum series, first we're just going to pull the largest value in each year. This is going to give us 108 values that we can use as a sample to estimate the probability distribution of the largest flow in each year, or the annual maximum. So let's take a moment to be reminded of the assumptions that we're making in this data set of 108 annual maximum values. Right? So we're treating this sample as a random representative sample from the probability distribution of the largest flow in each year. We're assuming the sample is IID, which stands for independent and identically distributed. Right, identically distributed just means all the values either come from the same probability distribution or can be effectively represented by the same probability distribution. Another way to say that is the data is homogeneous, and because we collect data over time, the data is also stationary. We're assuming that the sample is adequately representative of the population, but at the same time, we're keeping track of our uncertainty in that assumption and knowing that the estimate of our probability distribution is going to improve with sample size, and noting that the sample size we have is 108 years. So let's get a look at what this probability distribution might look like based on our sample of observations. Here's a histogram of the data. We are seeing that most of our flows are here at the low end, and with a couple of values, though, that are many times greater than most of them. We saw in the introductory lecture that we can sometimes more effectively model flow in log space. So here's a histogram of the base 10 log flows. And as we can see, it's a lot more symmetrical and friendly. So We're going to continue with flow in log space. So the histogram, as a reminder, is an estimate of the probability density function, or PDF. So quick flashback to two of our forms of representing a probability distribution. We have the probability density function here on the top, the bell curve form, where the curve shows us where the curve is high, we have the greatest probability density, meaning the greatest likelihood of seeing values of our variable in that range. The cumulative distribution function, or CDF, is just an accumulation of probability across the range of our variable, ranges from 0 to 1. It can be the probability less than, it could be the probability greater than. And we also sometimes show this in a frequency curve form with the axes reversed and adjusted, and we will walk through that next. So if we want to estimate the cumulative distribution function with our data, we could choose to just accumulate the histogram, but instead, so we saw in the introductory lecture that it can be more effective to estimate the cumulative distribution function by plotting all of the sample members versus plotting positions. Right, so plotting position was just an estimate of the cumulative probability of each sample member, and it's based on the sample size and on the position of each sample member or observation within the sample that's been sorted by magnitude. So effectively, we're just computing the relative frequency of being less than each sample member based on how many of the observations were equal to or less than each observation. The rank is the count of observations that are less than or equal to, so M rank over N sample size is our estimate of the probability of being less than the sample member with that rank. So quick reminder, the plotting position is not quite as simple as rank over sample size, because either the largest or smallest value will have a rank of N, and we'll get N over N equals 1, which is not a good probability estimate. So there are many plotting positions, and each of them with an adjustment of rank over sample size. We look most often at Weibull and median. Each of the plotting positions, there's maybe a dozen others, aim at a certain characteristic of the probability estimate. So for this example, we'll walk forward with the Weibull plotting position. What we have in the table is the largest 14 values and the smallest 14 values out of our 108. And they're sorted by flow. We see the rank, we see the computed plotting position, the non-exceedance probability in this case. Here's the smallest values with rank of 1 down here and computed plotting positions. So when I plot these, I'm going to have a red circle around one of the points just so we can follow through the plots with their changing axes. So the value of 105,000 CFS has a non-exceedance probability estimate of 90%. We'll have that circled in each of the plots. So here's our data plotted like the CDF shown in the previous slide, where we've got flow on the horizontal, we've got the cumulative probability on the vertical, and here is our circled value at 105,000 CFS. To plot the frequency curve form, the first thing we do is we switch the axes. So we're going to put flow on the vertical and probability on the horizontal. We're going to switch this linear probability axis to a normal probability axis based on the normal distribution. We're going to change the flow axis from linear to a base 10 log scale. And now we see our data. We've still got this circled point over here. We see that our data is approximately a straight line, and that's not that surprising if we think about the histogram that we made of log flow. So a normal probability axis will show data as a straight line if that data is normally distributed. And so this is showing us that the base 10 log of our data is somewhat normally distributed. The next change we're going to make is to switch from cumulative annual non-exceedance probability to cumulative exceedance probability. Right now, note this is annual exceedance probability because we've got the largest flow in each year, right? So we're building annual probabilities based on that time step. Having gone to exceedance probability, we can plot return periods as well. The return period is just 1 over exceedance probability. So our value circled here, the 105,000 CFS with a 10% non-exceedance probability, is just based on estimating that plotting position from the fact that the value has been equaled or exceeded 11 times in 108 years, right? And a similar assumption for our largest point is we can plot it only by estimating that it was the largest value in 108 years. So what can we do next? Well, we can just draw a graphical probability distribution, which means I've just taken my pen to paper or taken my cursor to screen and drawn in a probability distribution. Does not have an equation, does not have parameters, right? This is just a line. And this can give us a good fit to our data, but the problem with it is if we're interested in flows that are beyond the range of our sample. Right, so another option, especially for unregulated flows that look this smooth, is to fit an analytical probability distribution. Right? So we can fit an analytical probability distribution, or what's called a parametric model, as you saw in the previous lecture. And this will allow us to take a quick look at our federal guidance for annual maximum unregulated flows. So here, this red line I've added is the fit of a log Pearson type 3 distribution to our 108 years of annual maximum flow. I'm going to talk briefly about Bulletin 17B and C, which is our federal guidance that suggests that we use the log Pearson type 3 distribution. We're going to have a lecture later tomorrow, which is much more information about Bulletin 17B and C. I will just say a few things about it here because you're going to see it in workshop number 2. Right, so Bulletin 17B is the third or fourth in a series that was published in 1982. And more recently, now we have Bulletin 17C, which we published in February of 2018. The main difference between the guidance in 17C from B is the fitting method. We're still fitting the log Pearson type 3 distribution, but we're doing it in a different way. Just a few details about the Bulletin 17 guidance. The federal guidance suggests that we estimate a log Pearson type 3 distribution from the annual maximum series. Suggests we use the method of moments to estimate that distribution, which, as a reminder, means we use the moments of the sample of data to estimate the moments of the distribution. Bulletin 17B does that with product moments. Bulletin 17C still uses product moments, but it uses an algorithm called the expected moments algorithm to do it. Now, there's more to the guidance than just saying which distribution to use on which data. There's also some adjustments to be made for difficult data. For example, missing data or low or high outliers within the data set, and also for zero flows. Zero flows are a problem because the logarithm of zero is undefined, but there are some streams that are dry for a few years in a row, and so the annual maximums are zero. So there needs to be a way to handle those, and that is part of the guidance. The guidance also allows us to use some additional information that can help improve the probability estimates. So there's methods for using regional skews, for using historical or paleo information about large floods that have happened in the past, or the fact that no large floods have happened in the past. And there's also approaches for using longer record site nearby to improve the probability estimates for a short record site. Right. So that's all I'll say about Bulletin 17B and C for now, and we'll have another lecture on that later. However, one more thing that we want to include with our parametric model or our analytical probability distribution is some description of the uncertainty, right? The uncertainty here is based on the fact that we have a limited record that might not be representative of our distribution. And so we can draw, in this case, a confidence interval. 90% confidence interval, simply put, means we're drawing an interval that we believe has a 90% chance of containing the true distribution. Right? So that's unregulated flows. I mentioned this site is below a reservoir, so we're also interested in the regulated frequency curve or the probability distribution of regulated flows. Right? This is a reservoir that holds a flood pool empty so that when a large inflow comes, the Large inflows can be stored, increasing the level in the reservoir and holding the release here in red at a safe channel capacity until the inflow has dropped below that safe release. And then the water is continued to be evacuated at that release until the flood pool has been emptied. So we're interested in building a regulated frequency curve. We can do it in the same way we did an unregulated frequency curve. We have a gauge record, and the values in red are the gauged flows below the reservoir. So this is a shorter record from 1955 to, well, in this case, only till about 2005. We can pull out our annual maximums and do a frequency curve of this data. But we have two issues. The first is, are we looking at homogeneous data for the regulation? Meaning, was the reservoir operated in the same way for this entire period? And it's fairly common that it would not be, right? So if the operation isn't homogeneous, then we don't have a homogeneous sample, meaning it's not identically distributed, it's not stationary. Another issue is that this is a shorter record. This is a 50-year record as opposed to the 108-year record. So one way we can handle both of these issues is to use a reservoir simulation model, which can simulate current reservoir operations, and then we can route our entire period of record of data through the reservoir simulation model. That will allow us to be sure we have current and homogeneous regulation, and it will also give us a larger data set. So here in light blue, we have simulated reservoir releases routed to the downstream location from the reservoir simulation model. Now, it isn't actually the entire period of record that got simulated. It's only 81 years of the period of record. But it is still longer than the original gauged flows, and it is a consistent operation. So in the same process as with the unregulated flows, we're going to pick out our annual maximums. Our data set now, instead of being these 108 annual maximum unregulated flows, we're going to have 81 regulated maximums. And we do a frequency analysis of those by sorting them, ranking them, and plotting them against plotting positions. So our original unregulated flows are now the hollow diamonds, and the blue is our regulated flows. Now, we can see a little bit more clearly now that we've got some thresholds. This lower threshold at 4,000 CFS is, I think, a hydropower flow. This upper threshold at 115,000 CFS is that channel capacity. And what we're seeing here is that in our period of record, there weren't any events large enough for the volume to have exceeded the flood pool in the reservoir and called for a release beyond the channel capacity. Right, so we only have flows that are topped off at this 115,000 CFS. Right, so what should we do next here? Well, with the unregulated flows, we fit an analytical probability distribution. What would happen if we did this to these? Right, here's an analytical fit of a log Pearson type 3 distribution. We can see that this distribution does a very nice job of smoothing through our data, but therefore does a fairly poor job of respecting the thresholds down here at 4,000, up here at 115,000. So this is not at all a good representation. In the case of regulated flows, it is a better idea to use a graphical frequency curve, right? So I can draw it flat at relevant thresholds. I can smooth through some data points if I think there's sampling error, but I can go flat again and respect a threshold up here. Right, so a graphical curve is a better approach, but it does leave us the problem of what to do beyond the range of the data, right? If we're interested in larger events with lower probabilities, we don't really have a method to extrapolate here, right? We have a range that we need to make estimates on the probability distribution. What we generally do here is we go back to our reservoir model with some synthetic hydrographs that are constructed to have a particular exceedance probability, right? So this is going to be the topic of our next video, right? So we're going to construct synthetic events that have a specified frequency. The way we do this is to estimate families of frequency curves that are longer duration average flows or volumes. We're going to scale up some historical event to the given frequency based on those longer duration averages, and we're going to route that event through the operation model. Another important assumption that we're making here is that the likelihood of the peak release is equal to the likelihood of the inflow that we routed through. Okay, that's not always true, and so it's an important assumption to keep in mind. And because that part of the analysis is going to be in the next video, I'll just show you a quick preview that we've here built two synthetic hydrographs at 200 and 500 year, and was able to draw a connection of the regulated frequency curve up to meet the unregulated. So that is the end of the first video. In the next video, we'll be talking about annual extremes again, but longer duration flows in order to be able to construct those synthetic hydrographs. So I will see you in the next video.